You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dan Werthimer. Dan Werthimer is the co-founder and chief scientist of the SETI at Home project at the University of California, Berkeley. He specializes in signal processing for radio astronomy. He has been doing SETI since 1979, and he runs the Serendipitous, Optical SETI, and Casper projects. Remember to subscribe to Event Horizon so you never miss an episode.
Dr. Dan Werthimer, welcome back to the program.
Nice to talk to you, John.
Now, Doctor, we have had a lot of hullabaloo on YouTube about the BLC1 signal, which, as we both know, was an interesting signal for sure. But at the time that it was published, there was a concurrent paper published at exactly the same time by many of the same team members saying, we think we know what this is, which is useful because that tells SETI what to filter out. Whenever you see a weird kind of interference you haven't seen before, and you know it's from Earth, then you can filter it out. And that's where that signal sat, as far as I know. Are you aware, with all the sensationalism that's going on, are you aware of any new development regarding that signal anywhere?
There's no new development. Nobody's paying any attention to it because it was shown super clearly that it was a radio interference. And as you know, it's a big problem in SETI that there's a lot of radio pollution. You're looking for signals from extraterrestrials. And we always are discovering signals from terrestrials, you know, cell phones and radars and satellites and TVs and Wi-Fi. And it's a huge problem. And the Earth is kind of a crappy place to do SETI right now. We might eventually, if we could afford it, we'd do SETI on the backside of the moon, where the moon would act like a big shield from all this radio pollution. Anyway, that BLC1, people were kind of excited about it for a little bit because they hadn't done the thorough interference test to figure out whether it was interference or not. Then they looked carefully at it, and they realized they were seeing the same signal at many places in the sky. ET would only look at, a signal would only come from a star or a planet. It wouldn't be like everywhere in the sky you look. So there are lots of techniques to figure out if the signal is interference or not, if it's caused by humans or caused by ET. But one of the techniques is you move the telescope across the star, and as you move away from the star, the signal should get weaker and weaker. And if you kind of sweep back and forth, it should get really strong when you're pointed right at it, and then gradually get weaker and weaker. And you shouldn't be able to see it at other places in the sky, but you do with interference, that human-made interference. It'll come in at lots of, comes in over the side of the telescope and gets into the receiver. And anyway, it was coming from many, many places. It's clearly interference, and there were a couple papers written about it. There's no question. Nobody's bothering to do anything about it because it's clearly interference.
So that type of interference is almost certainly Earth-based. So when you wag the telescope and you still see it, that would suggest Earth, right, as opposed to a satellite. Is that correct? Or can a satellite also be eliminated through the wag test?
Well, the satellites, yeah, it's an interesting question because there are different kinds of satellites, but almost always the satellites are orbiting the Earth very rapidly. They go around every hour and a half, or some of the really high ones, they actually stay at a fixed place above the Earth with respect to the Earth, but they're not fixed with respect to the stars. So if you look long enough, the satellites will be in a completely different position. And what Breakthrough eventually did was they went back through a lot of their data that they, taken over the years, and they saw that signal was coming from many places in the sky, not just one. But yeah, satellites are getting to be a major source of interference. I think the WOW signal is probably a satellite, but there are very few satellites back at that time. But now there are, I think, tens of thousands, maybe 20 or 30,000 satellites, and they're occupying more and more of the electromagnetic spectrum, the radio spectrum. They're filling it up. So it's very hard. It's getting harder and harder to do SETI from Earth, and some bands are completely unusable. If ET's transmitting in one of those bands, a TV band or a Wi-Fi band or a cell phone band, we'll never detect them at those bands unless we get far away from the Earth.
So far side of the moon, but and there are interesting ideas, for building radio telescopes. Nothing's funded.
Yeah, there are craters on the backside of the moon that are kind of parabolic in shape. Nice place to put a radio.
Almost looks like a radio telescope,
Yeah.
so you can just set it right in the hollow.
I'm working with a group at Berkeley. This is not my project, but I'm helping them put a small telescope on the backside of the moon that could lead to some cosmology, understanding the early universe. But it'll also help us. So there's some bands that don't even get through the atmosphere. Forget about the problem of interference from human civilization, but the atmosphere blocks a lot of different wavelengths that actually it's good in a way, like it blocks the extreme ultraviolet rays, which would be really bad for us and give us cancer, but it also blocks the low frequency radio waves, things below 20 megahertz. And we can't do SETI from Earth at those frequencies. So it'll be interesting right now, we're just doing a very small telescope, and there's no chance that we could have this thing detect ET, but it's leading, it's a prototype, and I think we'll get better and better at putting bigger and bigger and better telescopes on the backside of the moon.
Proof of concept, at least.
Yeah, exactly.
But, probing the early universe, though, that's good. That's good stuff, too. Now, with BLC1, the other claim, there were other claims. Another claim with that signal was that it was also originally a candidate from SETI at home.
Yeah, that was fabricated.
That was not
I don't
true.
know if Mr. Holland, the guy that made the YouTube, was misinformed and didn't check the information. It's just not very good at figuring out when he's being tricked or misled or whether he deliberately lied. But certainly that's not true.
No, and back in the day, SETI at home was my screensaver, and we'd have all known. Is there any chance of now? By the way, one of the most common comments I get when I make SETI videos is I was a member of SETI at home and ran that screensaver, and some people even had 20 computers at work running it and things like that. And there is still to this day, so many years later, a fondness for SETI at home because everybody felt like they were a part of the effort, in some small way. Is it still on ice? Can it be brought back? Is there anything that a revived SETI at home could do in modern radio astronomy with SETI?
Yeah, there only is talk right now. We've been talking to our colleagues in China that have the big FAST telescope, the largest radio telescope on the planet, about a SETI at home project there. We talked to other observatories, but the only thing we're doing with SETI at home, which is actually really important, is following up on the best candidates that the volunteers found. Some of these things, like we've been looking at about 200 of the very best things that repeat when you come back to the same place in the sky, and strong signals. I don't think any of them are going to turn out to be ET, but we always want to follow up on our best list. And that's what we've been doing for the last few years. But there's no, as you pointed out, there's no volunteer computing part of SETI at home. The other thing we've been doing is we've just finished writing 2 papers that talk about how we analyze the data and how we injected tens of thousands of different kinds of fake signals, fake ET radio signals, to make sure that we were analyzing the data well and optimize our signal detection algorithms. So they're kind of 2 very technical papers that talk a lot about all the different computer algorithms and ways we look for a rich variety of signals that'll be interesting for the nerds that are into SETI.
Yeah, I'm one of those. And let me ask you this. Now, say past data sets, early data sets, say things taken in the 90s and all that, before we really had all these crazy algorithms and ways to filter, can those be researched again? Can you go back and use an old data set like that?
Yeah.
Apply new methods, modern methods, and find something you might have missed at the time.
Yeah. In fact, for the SETI at home, we actually keep the original raw data set. We have a few petabytes. We stored at the National Energy Supercomputing Center, and that data is available to the scientific community. And we've actually gone back and analyzed some of that data because, like you said, there are new ideas, new kinds of signals to look for. Sometimes somebody finds an interesting thing and we want to follow up on it. We go back and say, hey, did we look at that place in the sky? We've covered, about a third of the sky with SETI at home. And so we have observations that we can go back and check on. But in our signal detection algorithms, that when we go through our database, we keep improving those. We keep improving, as you mentioned, ways to reject the interference. We get better and better at that. And we keep on improving our signal detection algorithms that become more sensitive or look for a new type of signal. But not all SETI programs are able to keep the original raw data. So some programs, you can't really go back and redo the analysis. They keep some maybe subset of the data or some, because it's a lot of data to keep the raw original data. So some of the SETI programs that we do, we can't really go back and reprocess in a good way.
How did SETI at Home come about? What was the motivation to try to build that interesting network? What was the early story? Because I know you were the head guy. So how'd that happen initially?
Well, I wasn't a head guy. There were 4 or 6 of us, depending on your definition. We all worked together. We built a really fun team. It came from a couple different directions. So I don't just do SETI. I work on pulsars and fast radio bursts, and we were doing. I was working with a pulsar group at Berkeley and also at Cornell University, and to look for pulsars, it's similarly kind of constrained. You want a lot of computing power, and when people went home at night, they had a lot of computers in my lab. There are a few hundred people that work in the lab, and when they went home at night, we started using their computers for pulsar searching. And then we started using computers in other buildings on campus. But that was just pulsar work. And then a friend at David Getty in Seattle, he was a student of David Anderson, who was a computer science professor here at Berkeley. So David Getty was at a cocktail party, and they were thinking about what kind of projects would engage the world. And David Getty he's a computer scientist. He was working at Microsoft at the time in Seattle. And he was thinking about SETI might be a good thing. And he had this idea that you could engage the world in a distributed computing project where people could volunteer in that. So we've been doing kind of computing just with computers in the building and other buildings at our university. But he thought of this idea that we could engage the public in SETI. Then they reached out to an astronomer in Seattle, Woody Sullivan, and Woody knew a lot about SETI. He was one of the pioneers of SETI. And Woody said, "Hey, Dan, you should talk to Dan because Dan's got a lot of data. He's doing this big SETI experiment at Arecibo." So they talked to us, and I thought about how we could use use this thing in distributed computing and put together some ideas. And we formed a team at that point, and that was the kind of how SETI at Home got started.
Now, with today's equipment, and one of the things that actually shocks me, you remember the big ear and the wow signal and all that,
right?
Where you had this receiver that had a 10
yeah,
kilohertz.
I worked for a little bit with my colleagues at Ohio State, and they used one of our SETI machines there.
Yeah, actually, I've had 2 of the basically all that's left of the wow signal discoverers on the show. I had Jerry Eman and Bob Dixon.
Oh, nice.
Yeah. So I tracked them down, or more accurately, Ross tracked them down. But the thing is that that receiver was 50 channels, and now a modern SETI receiver is 800 million.
Billions. And of course, we have hundreds of thousands of things that look much better than the wow signal, just because we're doing a much more thorough search. Not because we're smarter, just because, as you were saying, the technology changes so fast, and we're taking advantage of all that stuff that comes out of Silicon Valley. I think that wow signal is extremely unlikely to be anything to do with ET. I think it's much more likely interference. When they designed that SETI experiment, and when John Krauss designed it, they were very clever about a system to reject interference. They looked at 2 different receivers looking at different places in the sky. And when the Earth turns, they expected a signal to first go by the first receiver, and then as the Earth turned a little bit more, it would go by the second receiver. And they get the signal getting stronger and stronger as it went over the first receiver, and then weaker and weaker as it went away. And then it should be picked up in the second receiver, and it would get stronger and stronger. And when they wrote down how their SETI experiment was going to work, they said, before we get excited about something, we should see it in not just the first receiver, but we should then see it a little bit later in the second receiver. And they never saw it in the second receiver. And so right away, it sort of violated their whole way of rejected interference. But they got excited about it anyway. But it was some kind of interference, a transient interference, and probably a satellite. So, it's been looked at a lot since then, and I think you pointed out that it's not really interesting if you can't ever see it again.
If you never see it again, but that makes our Arecibo signal we sent out uninteresting to aliens because we never repeated. But at the same time, that was just a token.
Yeah, I mean, you could look at it. That signal that was sent out when the Arecibo dish was resurfaced, they were just kind of celebrating it, and they thought it'd be a fun way to celebrate. That is, maybe ET, it would get their attention. By the way, you probably know it was sent to M13, a globular cluster with a few million stars, but that thing is 25,000 light years away. So it's going to take 25,000 years to get there. And if they want to send a message back, it's 25,000 years to get back to us. So, set your clocks for 50,000 years from now, minus 20 years, sent in 1970, minus 50 years. So anyway, I would imagine if ET saw something like that, they would get interested, and maybe they would, then look and see all the other radio signals that we're sending all the time, the BMUS radars, and we have very powerful signals leaving the Earth, and they could detect oxygen in our atmosphere. So even though that little thing was only sent, I think, for 2 minutes, it might pique their attention, and they might spend a little more time looking at it.
Now, about that signal, the Arecibo signal, though, how targeted was that towards the globular cluster? Now, I want to say globular clusters may not be very great for life because you got all these stars packed in close, high radiation environment. So, you got to wonder about that.
Right.
But was that signal so narrow, not narrowband? Well, it was narrowband, but
right. It was, that signal is 2 arc minutes across, which is, but maybe your listeners don't know. An arc minute is 1/60th of a degree. So 2 arc minutes would be 2/60ths, or about 1/30th of a degree. So it's a pretty tight, very narrow beam. It's not illuminating a big chunk of the universe.
And it's yeah, exactly. But it was also through a trick of Arecibo's transmitter. It was able to be very powerful just for a moment, right?
Yeah, so that's a megawatt transmitter. But the thing is that megawatt transmitter is connected to a really big dish, it's 1,000 feet across. And so it's that we say it in the electronics language, it has a lot of gain. So if you take a megawatt transmitter and you put it in an omnidirectional antenna that just sends, that where the signal goes off in all directions, then it would be quite weak when it gets to out at interstellar distances. But if you beam it with a giant reflecting mirror, a parabolic mirror like the Arecibo telescope, then it's, of course, much more powerful. So it's not like a megawatt transmitter that's beaming every which way.
Well, that's interesting in and of itself, because the original beginning, so to speak, of SETI, even though it kind of sort of wasn't, but was the Kokonian-Morrison paper back many decades ago, where they were envisioning a beacon,
right,
and presumably omnidirectional beacon that everybody would see if they looked for it, which we never saw any such thing. But there's probably a reason for that, because that's a bad waste of energy when you can send out directional signals, right? But Earth has been screaming its biosphere for billions of years. So it might be a target that you would shoot a targeted signal right at. And that's what you're looking for, right?
Yeah, so in SETI, as your question points out, there are different things you can look for, these technosignatures. And one would be like exactly what you're saying. Something was intentionally beamed toward us. They know about us. They've seen our radio signals. They've seen oxygen in our atmosphere. Maybe they've been watching I Love Lucy or Ed Sullivan or our early TV shows. So that would be a deliberate. But then the other possibility that I think is actually more likely, if we ever detect them, would be some artifact of their civilization that they just sort of accidentally, leak off their planet, much like we have all this radar and navigational beacons and radio and television that wasn't really meant for interstellar communication. It's meant for human-to-human communication, or radars to detect, incoming ballistic missiles or something like that. Those are probably, in my opinion, the most likely thing that we would first find another civilization. There are other kinds of technosignatures that you can find. There are biological signatures, which I think are very promising now to look at the atmosphere of a distant planet. If you detect oxygen, that might indicate there's photosynthesis going on, trees, plants. And so you might be able to detect extraterrestrial biology. You might be able to detect, there may be other ways to detect a technological civilization besides radio waves. There are a lot of proposals. We've been looking, as you know, for laser signals, optical, in the optical wavelengths. There's a pretty good chance that we've got it all wrong in SETI. A lot of really interesting, the most interesting discoveries in astronomy are made serendipitously, accidentally, pulsars. Nobody speculated there might be anything like pulsars, and Jocelyn Bell, a graduate student, found these little glitches in the data. Her professor just said, "Oh, those are cars driving by and spark plugs." But she pursued it and figured out that these are the whole new astronomical phenomena. Gamma ray bursts are like that. A lot of the Big Bang, the radiation from the Big Bang was found by people studying noise in the transatlantic cables. Yeah. So all that, a lot of these discoveries are made accidentally. So I think SETI is likely to fall into that category. So, if you'd asked people 200 years ago, what should we look for? They didn't say radio signals. We didn't know about radio. They said, set big fires on the planet, and ET would see the fires, or use mirror to flash them, reflect sunlight to ET, or they said build some large geometric structures, squares and circles and triangles, and ET would see that we, see these big geometric structures. Anyway, all those early ideas we kind of laugh at. There were people that were listening for ET, Marconi, Tesla, were listening for radio signals that don't even get through the ionosphere. So there was no way that ET could have sent a signal at those frequencies. So anyway, now we kind of laugh at all that stuff. So that means 200 years from now, people will be laughing at what we did. They'll say, oh, why didn't Dan use tachyons in subspace communication? That doesn't mean we shouldn't look. You still got to do the best thing you can do, and maybe we'll get lucky. But it wouldn't surprise me if it'll be some kind of accidental thing. It won't be somebody like me deliberately trying to figure out, are we alone? Is anybody out there? It'll be maybe some dark matter experimenter or some physics experiment or something like that.
There's a fun story from the very early days in the 19th century, ideas about METI, which really isn't SETI, but SETI, with Nikola Tesla picking up weird signals that he wasn't aware of.
Right.
And one of the theories was that he picked up Marconi testing his.
Well, that's a fun story, but he was actually listening to distant lightning bolts, and lightning from a few thousand miles away. The lightning doesn't give off just flashes of light, but flashes of radio waves. And when the lightning bounces around between the Earth and it gets dispersed, and it turns out the high frequency radio waves come in first and the low frequency waves come in later. It takes them a little longer to get to Marconi and Tesla. And what they heard were, they called them whistlers. That it starts off high, and they heard that and they thought that was ET, but that was lightning.
The fun thing about lightning that anybody in the audience can do is turn on your AM radio during a thunderstorm. And you will hear.
Oh, do you hear the whistlers?
No, you don't hear the whistlers. What you just hear is static every time there's a lightning bolt.
Right.
And so it must bleed over, because obviously lightning is hugely broadband, right. And it bleeds over. So you're listening to the radio, and then boom, all of a sudden you hear a lightning bolt. Come through.
So if the lightning is close, you don't get a very big difference between the high frequencies and the low frequencies. So it would come in as a click like that, like you were talking about. But if it's a little further away, it would be a very fast. You might be able to hear a little chirp up, but if it's very far away, it would take a long time. The difference between the high and the low frequencies would get a lot. The low would come in, so it'd be more of a. Anyway, so you can tell the distance from lightning by that chirp.
Interesting stuff. And another thing that I did, obviously amateur radio astronomy is extremely hard, but there are people who have done it. And I am one of them, but it was a very, very simple, simple experiment as a teenager from a design that I found, I believe, either in Sky and Telescope or Astronomy Magazine. And this would have been 1989, 90, where you can take a piece of metal fencing and put a big copper loop on it, connect it up to your shortwave radio, and look at a certain area of frequencies and hear Jupiter. And I successfully did it because it sounded like ocean waves. And that's what it was supposed to sound like. So I assume I was successful in hearing Jupiter. So there are things you can do in radio astronomy just to play around.
Yeah, that's great. I think since you did that, I think now there are kits where you can build stuff in your backyard and stuff and look at a few sources. There are not that many things that are really bright enough in the sky to see with a very small radio telescope. But, Grote Reber, he built this giant dish in his backyard back a long time ago, almost 100 years ago. That was kind of getting radio astronomy started. So it is possible to build stuff in your backyard. But just a thing that's like a few feet across, you can make it out of wood. And as you were saying, you put chicken wire or something to metalize it, make it reflecting. You can do something with that kind of size. You can look at a few sources. We have some little things on the roof of our building where the students use that are kind of like a yard across, and they can look at a few pulsars and make measurements.
It's interesting. It's not as inaccessible as you might think, although Optical SETI probably is. Probably not going to be able to do that on an amateur basis.
Well, it turns out detectors that we use to look for these very short flashes of light, a billionth of a second long, a nanosecond, they are now, $5 for the detector. And we were thinking about, could we make a little kit for amateurs where they could move their telescope around and put one of these things on the back of their telescope. It's the detector plus some electronics, and you hook it up to a laptop. And it's not $5, but you could build it for maybe a few $100s, and amateurs might be interested in doing that. We could have some kind of citizen science project where we, amateurs could look at a bunch of different stars. Each one could cover, 100 or 1,000 stars. And if we had 1,000 amateurs, we could do 1,000,000 stars.
You know what? I'm excited. I want to do that. So I could mount this thing on my Celestron and have it, it's clock drive and all that stuff, so I can track and send citizen science data even when I'm not even using it. I would love that.
Yeah, the detectors used to be really expensive, but they got cheap, not because astronomers are buying so many, but they're used in medical science. There are these things called positron emission tomography machines, PET scans, looking for tumors to see if you have cancer, where the cancer is, and that you swallow a radioactive dye. It goes to the fast-growing cells, the cancer cells, and though that radioactive dye emits particles, and they use these detectors they surround your body with these detectors, and they can figure out where the tumors are. And it turns out we can use those photon counting detectors for SETI, and that's made the whole thing cheap.
Interesting. And it's worth noting, too, that PET scans are particularly interesting. Positron emission tomography, now think about that. That is humans harnessing antimatter. We already do it with the positron. And it's actually used in our technology, and not as so futuristic as people might think. Now, making a lot of antimatter is a problem, but positrons, not so much. Now, broadening SETI. So we tend to right now, we have targeted searches, but there's also the option of all Sky SETI and very broad fields of view that are coming online. And I know you work in that, PanoSETI and things like that. What's the state of that? What experiments are going to come online that just broaden our horizons as far as what we can look at?
Right. Okay, so all Sky, as you just pointed out, is very interesting to me. So maybe the history of fast radio bursts. There are 1,000 of these things that go off every day, but nobody found them until I think about maybe 15 years ago. They were just discovered by accident. Somebody happened to be pointing a telescope in the right direction at the right time. But if we could have telescopes that looked at the whole sky, we would have known about fast radio bursts a long time ago. And they turn out to be really interesting scientifically. We can actually weigh the universe with fast radio bursts by looking at the same thing. We were talking about lightning, the dispersion. This thing, when the burst goes off, it travels between all the galaxies. And depending on how much stuff there is between us and the distant fast radio burst, and they're often at very long, they might be many billions of light years away. We can, by that dispersion, the amount of that chirp, we can measure how much junk there is between us and the FRB, the fast radio burst. So that's how we can weigh the universe. So anyway, they're interesting for a lot of reasons. And then we didn't know about them because our telescopes look at 1/1,000,000th of the sky at a time. So if you're pointing in the wrong place, you're going to miss it. So if we're looking for these flashes from ET, it's really hard to know where a flash. And if the flash is happening once a month, and we're pointing one place and the flash is coming from another place, we're going to miss it. So actually, this was thought of by the Russians in the 50s. They started thinking about all-sky radio experiments, and Troitsky and Shklovsky worked together, and they built the first all-sky radio experiment. It wasn't very sensitive. It was very small antennas, but it was a really exciting idea. And it was interesting that when the Russians met the Americans for the first time, because of the Cold War, the Russian scientists and the American scientists Western scientists were kind of isolated from each other. We didn't know what they were doing in SETI, and they didn't know what we were doing in SETI. And we had very different ideas about, what we should look for and what kind of signals it would be. And that's another reason why I think we're probably doing the wrong thing. If two sets of, people that are both human, both evolved on the same planet, have completely different ideas, then for sure we're doing the wrong. Anyway, so I think it'd be really interesting to do all sky radio, and it'd be interesting to do all sky optical and infrared searches. And I and a few other colleagues have been thinking about how we could do an all sky radio experiment. There's different ways to do it. There's a couple of different really exciting technologies to do that. And actually, it turns out I'm working with some Chinese colleagues now who are going to do that experiment, an all sky radio experiment, although it'd be a pretty small telescope at first, but they hope to expand it. And then, as you know, because I think we've talked about this before on one of your programs.
Yeah, indeed.
We're doing this PanoSETI experiment, and the idea is kind of fly's eye, have a bunch of telescopes all poking out in different directions. And each of our PanoSETI telescopes covered 100 square degrees. And if we could build 100 of them, we'd cover 10,000 square degrees, a pretty good chunk of the sky. And if we could, put 100 in the south and 100 in the north and 100 on the other side of the Earth, we could cover the whole sky. So we don't have the money to do 100. We have 3 right now, but we just got the money for 10 in a very bizarre way, which I'll tell you about, something that we didn't expect, but we're going to have 13 telescopes pretty soon. And that means we'll cover maybe, 1,000 square degrees on the sky. So we're getting there. So I'm excited about that. And I think if ET is sending these pulse kind of signals with a kind of that only happen once a day, once a week, once a month, once a year, then we really need to do all these all sky experiments. And there may be all kinds of astronomical phenomena that we discover. Whenever you look at the sky in a new, in this case, we're looking with a new time scale, nobody's really looked at the sky very well. It's very largely unexplored. Most astronomers, they have these cameras and they open the exposure time for hundreds of seconds or hours so they can look at very faint things. And they would never see these little flashes that are 1,000th of a second or a millionth of a second or a billionth of a second. And whenever you look at a kind of new parameter space, a new size scale, or maybe a new part of the electromagnetic spectrum, a new wavelength, a new frequency, or in this case, a new size scale, there's phenomena to be discovered. We don't understand why nature does this, but it sort of populates all possible size scales and wavelengths and time scales seem to have phenomena there. So we hope, we don't know this for sure, but that just by looking at this new time scale, we'll find some new things, maybe not ET, but hopefully some new astronomical phenomena.
Who knows what time scales extraterrestrials operate on, because it could be very short, as you just said, but also very long. It may be, they can't conceive of sending out a radio signal any faster than once every 100 years or something like that. And I remember this came to my attention from a very, very old magazine, which it cast your mind back to like 1980, Cosmic Quest magazine.
Oh, yeah.
And,
that was great. That was a great
magazine. It was.
I think that was published by Ohio State University. Yeah.
It is. And Jerry Eman actually still has it on the Big Ear Memorial website. So anybody that wants to read that magazine can go there and get it for free. Uh-huh. But the thing is, which is what I did, but the thing is that was floated a long time ago by, I believe, Frank Drake, that we don't know what time scale ET is operating on. And that was 40 years ago.
Right.
And here we are still playing around with the idea. But it is a problem within SETI. But there are many problems within SETI because,
it's an interesting problem. This time scale of a human lifetime is somewhat arbitrary. You probably know about this thing called the Long Now Foundation. They're trying to get people to think about long time scales. I think one of their projects is a clock that chimes every 1,000 years, and thinking about they're building a library of things books that will last tens of millions of years, trying to get people to think about not just the next quarterly profits or something like that, but let's think about longer time scales, think about how to save the earth and keep it going for another billion years or so.
That's a pitfall of humanity, is short-term thinking, because it is very difficult to create a political system that can think longer than an election cycle. And that's just reality. It's just reality.
Yeah.
But at the same time, it also sort of hinders long-term projects. So you kind of got to get the ball rolling pretty strongly, get the snowball going down the hill if you want to get something done, like, for example, the interstate highway system in the U.S. But if you're thinking about things that are going to take 300 years to come to fruition, very hard to convince anybody to fund that. But that's what we're dealing with here with SETI largely, right?
Yeah. I think kudos go to the National Science Foundation, who they funded gravitational wave research for, I think, maybe about 50 years. And everybody said, oh, they kept working on it and didn't see anything. And they kept funding it. And now, we're learning all kinds of things from these gravitational wave detectors. It's really opened up a whole new era in radio astronomy.
And it's only just started. Now, you wrote a paper, or you were a co-author on a paper recently about using CubeSats to look at gravitational waves.
Oh, yeah. Let me tell you about that. But because we're talking about panel SETI, I want to tell you a little bit more, if you don't mind.
Yeah, sure.
About how we were able to build 10 more telescopes and where the money came from. It didn't come from astronomers, actually. So, well, maybe, but something that we didn't expect at all. So, when we're looking for these like laser flashes from ET, there was kind of the equivalent of RFI radio interference in optical studies. So you get these flashes, but they come from they're atmospheric flashes. When a very high energy particle hits the atmosphere, gamma ray, cosmic ray, hits the atmosphere, it causes this flash of light. And we thought, we got to figure out how to get rid of this stuff. It's not ET. We don't want to pay any attention to it. It's kind of like how we kind of have to figure out how to get rid of radio interference, this optical interference, these flashes from, it's called Cherenkov radiation. Anyway, so we figured out a way to get rid of it. But the people that are studying this stuff got in touch with us, because it turns out our panel SETI telescopes are really good at finding this stuff. And we are trying to get rid of it, but it's their science. And there are a couple of really exciting things that they want to work with us on. One is that these very high, ultra high energy gamma rays they have energies that are 100 times higher than the highest energy particle accelerator, the Large Hadron Collider at the CERN. Humans can't make anything like this. They're peta electron volt energies. We have no idea what's causing them. And panel SETI actually is a really good telescope, because we have lots of little telescopes. You don't need a big, huge telescope to find these things, because they're really higher energies. You can use our small panel SETI telescopes. But anyway, they want to build 10 of them, and then they'd like to build a big array with 100 and figure out what's the source of these really high energy particles. And then other scientists that we hadn't expected at all, that are searching for dark matter. We don't really know what the dark matter is. Nobody knows. But one of the ideas is that it's probably some new kind of particle, and the particles would be occasionally smashing into each other. All the particles are jiggling around. They have thermal motion. And the dark matter would be like that, and it would occasionally, they'd hit each other and annihilate, and that would give off these gamma rays that we should be able to detect with panel SETI, and we could maybe shed light on dark matter. So anyway, those people in Germany, the dark matter researchers, they found some money to build a 10 telescope panel SETI array, and we said, oh yeah, great, we'd love to build it, and we're going to work together, and we'll do our SETI and the transient experiments, and we'll do gamma ray experiments and dark matter experiments, all with the same telescope. Anyway, a long kind of story, but kind of fun, accidental science.
Sort of cross-disciplinary, but you hit on something that, I know a little bit about. The oh my God particle and the Amaterasu particle. And those were those high energy things. And I've interviewed the scientists involved with that. And particularly the Amaterasu particle is interesting because it came from nowhere, a void. So if it's a supernova creating these things, it isn't evident, but we'll find out. Now, with the what you guys are doing with BLC1 to sort of bring it back around full circle.
Oh yeah, and also, if you want, we could talk about the CURIOS project. You asked me about that, but I delayed it, the CubeSat thing.
Oh, actually, let's do that first because that's what I was interested in is the CURIOS project. All right, you can do that use that to study all sorts of things, and CubeSats are particularly interesting because you can build them with off the shelf parts, and they're very cheap to launch now comparatively to what they used to be, and you can deploy a whole ton of them. Can you use anything like that for SETI, like an interferometer array or something like that? I mean, is there any pathway to that with that concept?
Yeah, so we do want to actually, for this project, we want to build an array of CubeSats, not an interferometer, but we hope to build about 30 CubeSats. We're going to launch our first one next year. It's a test project. By the way, before I tell you about that, I am not a leader of this project. Jessica Liu, she's a professor in astronomy, a colleague. She's an expert on black holes, and her student Hannah Gulick, and there's a big team. I'm just part of it, just helping out with the kind of technology, the electronics, the cameras, that kind of stuff. But anyway, the project is, we want to find out how many free floating black holes there are in the galaxy. And we know about this black hole in the center of the galaxy. That one's pretty easy to find, and there are black holes in the center of galaxies. We know where to look. But there are probably a lot of smaller black holes floating around our Milky Way galaxy and other galaxies, but they're really hard to find. They're black, they're dark, they don't give off radiation. But there's a way to find them, but it's kind of tricky to find them. So what happens when a black hole goes in front of a star, it acts like a lens, a gravitational lens. The black hole has gravity, and it makes this like a telescope. It makes the star get a little brighter, actually a lot brighter, sometimes 10 times brighter. And so when the black hole passes in front of the star, you should see the star get brighter and then dimmer. And that gravitational lensing, kind of the brightening of a star, betrays the presence of a black hole. So we can find them kind of indirectly by looking for stars that get brighter and then dimmer. And we'd like to kind of take a census, an inventory, and just see how many black holes are floating around the galaxy. We can measure various parameters of mass distribution. We can learn a lot more about black holes, about these smaller black holes, not just the ones at the center of galaxies. But it's a hard problem because we don't know where the black holes are. So what you want to do is what we were talking about earlier. You want to look at a big chunk of the sky because you don't know where this thing is going to happen and when it's going to happen. So this is kind of an ideal thing. It'd be like an all-sky telescope, but this would be a telescope that's basically a camera that's taking pictures of the sky every 30 seconds or so, and then looking for these, what we call occultation or gravitational lensing events from black holes. And so, you want to build a wide field telescope that looks at a big chunk of the sky, and then you want to have a whole bunch of them that are pointing in different places. And we want to do this in space because the atmosphere kind of makes the stars blurry and twinkle. And so this CubeSat is not an expensive thing. I think it's 6 of these cubes. Each cube is 10 centimeters so that's 4 inches. Each cube is 4 inches on a side. And 6 of these together would be large enough to build this telescope that we want to build. And the Canadians have offered to take it up for us. They've got something else they're testing, a guidance system, I think, but they can bring our thing along. It's a small telescope with one of these beautiful cameras at the back. And if that thing works, that'll be the prototype for an array of, we hope, 30 CubeSats.
Interesting. But is there an application for SETI? In other words, could you use such a thing? Could you put CubeSats that pass the dark side of the moon, the far side rather than the dark side? Sorry, Pink Floyd got me excited. Could you block the Earth's transmissions through a CubeSat passing behind the moon and taking a measurement while it's doing that?
Yeah, so I think a telescope, as you point out in your question, does not have to be on the backside of the moon. It doesn't have to be on the surface. It could be orbiting the moon or just going around the moon. And that's actually cheaper. It's hard to get down on the moon. You can orbit the moon, but if you want to land on the moon, you have to slow down, and that requires fuel. And then it's complicated to land because you don't want to crash into the moon. You want your instrument to survive. anyway, it's much more complicated to land on the moon. There are reasons why we're doing this experiment on the backside of the moon, but a big chunk of it is that because the Chinese are landing stuff on the moon, we got to go land on the moon. I don't know, it's competitive reasons, but it turns out we can get a free ride to the backside of the moon. But orbiting the moon is a really good idea. When you're going around the backside, it's very quiet. The CubeSat, I think that would be a very, very small radio telescope. And I think, if you're willing to spend more money and build something that maybe unfolds, like an umbrella kind of thing, you could have a small dish that orbits the moon. But we could start with the CubeSat. I think CubeSat might be good to kind of test the deployable technology. Can you unfurl an antenna or something like that? But my guess is to do any kind of serious science, you would want something a little bit bigger than a CubeSat. But I could be wrong about that. It's always good to start testing your ideas with small telescopes and build your way up. And so that might be a good way to at least evaluate the technology, see how well it works. Can you unfurl an antenna? Different ways to do that. There are other problems like how do you get your data back? But if it's orbiting the moon, then it'll come back around so you can see it when it comes, in front of the Earth, where the moon's not blocking it. So you have to record the data. There's a bunch of technological challenges, but I think it is a good idea. And maybe we should start with CubeSats, but eventually I think we're going to need a bigger antenna.
A giant unfurling antenna, the bigger the better, of course. Another thing about gravitational lensing that excites me is you can turn that into a telescope. If you go out to the lensing point of the sun, which is way out in the outer solar system, but if you go out there, you can actually use the sun as a telescope.
Right.
And you could presumably do that with a black hole.
Yeah, and we don't know how to do that, but ET might, in 1,000 years, we'll know how to do that.
ET might.
And then you have a telescope the size of the sun, if you use the sun as a gravitational lens. You have to put your camera way out beyond Pluto. But yeah, so don't hold your breath on that. It's not going to happen in our lifetimes, but maybe 50 generations from now.
Unless you have yourself frozen or life extension goes very rapid from here on. Although I'm not sure I want to live that long.
I'm a little disappointed if you look at, I think eventually humans will live forever. And we think about maybe 100,000 generations, and I missed it by a few of living forever.
I probably did too. I'm pushing 50, so I probably missed it myself, but I'm okay with it. But there may well be people being born right now that will live twice or three times longer than we had ever had a chance. It's an interesting times.
Yeah.
Lots of pros and cons. The older I get, the more a nice, long, permanent nap sounds. Be done with it.
Not me. I'm 70. I've been doing SETI for about 50 years, and I want to do more SETI. It's a lot of fun. It's interesting. It's a great question.
That's true. Well, that's true. I would definitely like SETI, but I'll tell you what, the one that really intrigues me is microbial life. I want to see what is in the ice shell moons.
Yeah. And I think that is much more likely to happen in our lifetimes. Earthlings might discover life in our own backyard on Europa or Enceladus. They both have liquid oceans, warm oceans. They both have places where we think life got started in the thermal vents, and they're rich in organics, and it wouldn't be surprising if there's something swimming in their oceans.
Yeah, SETI will be serendipitous, but actually, you got two ways to do this, because not only do you have the idea of checking Europa and Enceladus and all of these moons, which Europa Clipper successfully launched, which can sort of do that, or at least start the ball rolling. But the thing is you still have the origin of life experiments going on, the successors to Uri Miller. And at some point, those scientists in their lab might crack abiogenesis, and out pops a microbe from, the test tube, the experiment.
Yeah.
And then we know this is how RNA forms, this is how this forms, how DNA comes about from that, and so on. And that answers our question. It's either easy or it's really hard. And there it is. Because if it's easy, the universe must teem with microbes. And that one I think we will solve within the next few decades.
Yeah, I'm optimistic about that one too. And I think it's a very exciting time, as you were saying, because we'll soon have things that can land on Europa and Enceladus and Titan and figure out if there's life there. And the interesting thing will be, how different is that life? If it's identical to the life on Earth with the same exact 20 amino acids, that just means that life just traveled from or maybe it came from Enceladus to us, and we're not really Earthlings. We're Enceladus-lings. They're rocks that fly around the solar system, and when a big rock hits the Earth, all kinds of stuff goes flying around the solar system, and so it is possible for life to travel on rocks between all these places. But if it's completely different kind of life, there are 200 amino acids, and we just happen to use the 20 that happened to be in the tide pool when life got started. But if it's different chemistry and biochemistry, then we'll know it's a completely separate, as you were saying, biogenesis, completely separate start of life. It had the origin of life on Earth was very different from the origin of life on Enceladus. And that, if we find two separate places where life got started, that means the universe is teeming with life. If it's in our own backyard, it's everywhere.
It may be a microbe, but it says we are not alone. And who knows what happens out there. Now, my last question for you is just a simple statement, just to kill this once and for all. BLC1 is radio interference from Earth.
Yes, definitely radio interference. All scientific community, everybody does SETI, astronomy community. It's not a controversial thing. No scientist thinks that it has anything to do with radio. We know clearly that it's radio frequency interference.
And that's that. Nobody's looking further into it because now that we know what kind of interference it is, we know how to filter it out.
Yeah, we keep getting better and better, but unfortunately, interference keeps getting worse and worse as humans keep building more and more technology.
Yeah, that's also, I mean, when I look at Starlink passing overhead, just the sheer amount of satellites, flying over when they do a launch like that, and they want to make a constellation of 10,000 or more satellites, which granted, it certainly has its use, but there are others planning other constellations. And I actually wonder at some point, when does it become difficult for them to find frequencies to downlink at that isn't being bled into by other satellites? That is another cost of this.
Yeah, the whole spectrum is completely filled up now, and if you want one of these bands, you have to pay a lot of money for it now. It's very expensive. So, it's getting worse and worse, as you've said.
Block it out with a moon. It's very convenient that we have one.
Yeah, it's a big one.
Yeah.
Biggest one in the solar system.
Fantastic. All right, Dr. Werthimer, it's good to talk to you again, and we'll do it again in the future, I hope. And keep on trucking. SETI is an exercise in patience, but if you find anything, there you go.
It was great to talk to you, John. I appreciate your very perceptive and interesting questions. Take care.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.